today what we want to do is to introduce the Hamiltonian formalism through a very easy example that we have already introduced on some other videos. In this case, recall that, well, in general, if you have a mechanical system, you can describe that system with a function named as the Lagrangian. Okay, the Lagrangian will be a function that depends on the generalized coordinates that involve the system. Okay, so in general, you have that Lagrangian is a function of qi, qi dot, and t, where I goes from 1 to up to n. Okay, these are the coordinates that describe the mechanical system. Okay, so for example, well, to introduce the Hamiltonian formalism, well, we are going to define, and you'll see later on why, we are going to define the pi as the partial of L with respect to qi dot. Okay, this pi is going to be called the momentum conjugate. Okay, a very appropriate name, but we will explain that later. In this case, this is going to be taken just as a definition for now. Okay, so first of all, you may notice that the Lagrangian depends on qi dot, so it depends on a function that it will we are taking the derivative from. So taking this pi will allow us to define another function that will depend on some other variables, but these variables will not be under the derivative operator. But we will see that later on. We're going to define that function. It will be the Hamiltonian, and you will see that more clear. Okay, so we are going to use an example that we have shown on previous videos. Actually, there was a video where we showed that the standard Lagrangian of a particle that is only under the influence of a potential V, it is described by the Lagrangian m over 2 x dot squared plus y dot squared minus b. Okay, in this case this is just in 2 dimensions. Okay, but we have a video where we showed that in polar coordinates we can express this Lagrangian as the next. It will be m over 2 times r dot squared plus r squared theta dot squared minus b, where in this case b is a function of r and theta, which are the new generalized coordinates of the system. Okay, again, one of the first videos of the channel shows how to get from this expression over here to this expression over here. Perfect. So what happens if we find the Euler-Lagrange equations for this Lagrangian? In this case, we will have 2 equations, one for each coordinate, r and theta. Okay, so let's begin with r. We are going to have that the partial of L with respect to r is going to be mr theta dot squared minus the partial of v with respect to r. Then we will have that the partial of L with respect to r dot is going to be mr dot, and we will have that the derivative with respect to time of the partial of L with respect to r dot, it will be mr dot dot. So if we combine this in the Euler-Lagrange structure, we are going to get that this is mr dot dot minus mr theta dot squared equals minus the partial of b with respect to r. Perfect, and that will be the first equation for r. And for theta, we are going to get that the partial of L with respect to theta is equal to minus the partial of b with respect to theta, because of course here the kinetic energy term does not depend on theta, but b does depend on theta. So let's continue with the partial of L with respect to theta dots. That will be, well, m over 2, actually it will be mr squared theta dot. Okay, and then the derivative with respect to time of this is going to be Well, we have a product of functions of t. Remember that, of course, r depends on t and theta depends on t. So that means that here we are going to get m times 2r r dot theta dot plus r squared theta dot dot. Okay, so if we plug this in the Euler-Lagrange structure, we are going to get that this is m, well, 2m r r dot theta dot plus m r squared theta dot dot equals negative the partial of b with respect to theta. Okay, this will be the second equation of motion of, again, remember, we are studying a particle with mass m that is moving, but is under the influence of a potential v. Okay, well, the potential energy of this object is equal to v. Okay? Okay, so we just said that we can define a new quantity pi that is equal to the partial of L with respect to qi. Okay, so qi dot actually. So that means that here the term in the Euler-Lagrange equation that we found, this one, is actually that pi that we want to find. In this case, we are going to name that as pr. Okay, and the next is this one. This will be p theta. Okay, according to the definition we gave. So that means that we can take two new equations that are pr equal to mr dot and p theta equals to mr squared theta dot. Perfect. So this will be like another two equations that will be important. In this case, we can take that r dot is equal to pr over m and that theta dot is equal to p theta over mr squared. Okay, and first of all, let's look to these two equations of motion that we found. We see that, well, it has a dependence on the generalized coordinates differentiated with respect to time. In this case, for example, we have a theta dot here and r dot dot here, so we have the derivatives of the generalized coordinates. Again, we have the derivative of r here, the derivative of theta here, and 2 times the derivative of theta here. So that is what we want to avoid. That is the reason why we defined this new quantity over here. So we will be interested in taking out these all variables that depend, well, yeah, the variables that are being differentiated with respect to time. So how are we going to do that? Well, first of all, you see here that I already found what is r dot and theta dot in terms of these new variables p. Okay, but in these two equations we have, for example, r dot dot and theta dot dot. So this is not enough. So if we continue, we are going to get that r dot dot is just going to be equal to p r dot over m, and here, well, theta dot dot is going to be equal to, well, we can see this as maybe as a product of functions or a quotient of functions. So we are going to get p theta dot over mr squared minus 2p theta over mr cubed. You can verify. Okay, but look at from here, from this equation, remember, due to the Euler-Lagrange equation, we had that this was equal to the derivative with respect to time of, it was mr squared theta dot. Okay, we took the derivative of this product to get this, and we have that this is equal to negative the partial of p with respect to theta. Okay, so looking that we already know what theta dot is in terms of the p's, we can take the derivative with respect to time of that to get a new equation. So what I mean is the next. We are going to have the derivative with respect to time of mr squared times theta dot, but theta dot, well, is equal to p theta over mr squared. So p theta over mr squared, and again this is equal to negative the partial of b with respect to theta. As you can see, this will cancel, and we are going to get that p theta dot is equal to negative the partial of b with respect to theta. Another equation. Okay, perfect. So in this case, the only variable that is left is p r dot. So we need to find that. Okay, so to find p r dot, now we are going to use this equation that we have here. So we know that r dot dot is equal to this, so we are going to get m r dot dot, that is p r dot over m minus m r theta dot squared, but theta dot is this, so this is p theta over m r squared, and then this is equal to negative the partial of b with respect to r. Okay, perfect. In this case we get that p r dot minus here we are going to have p theta squared over mr to the third power equals to negative the partial of b with respect to r, and then p r dot is equal to negative the partial of b with respect to r plus p theta squared over mr to the third power. Okay, so everything we have done can be resumed in the next four equations. R dot equals pr over m, theta dot equals p theta over mr squared, this one over here, and p theta dot equals negative the partial of b with respect to theta. So the important thing here to notice is that we have the derivative with respect to time of every new generalized coordinate or momentum conjugate depending on the variables itself. I mean, every expression that we have here depends on r dot, theta dot, r, pr, or p theta. Okay, but we no longer have dependence on r dot and theta dot. That is the important thing. That is what we wanted to accomplish. Okay, and a very interesting fact that we can notice from these equations is that, for example, we can define a new function that will be called maybe k equals to pr squared over 2m plus p theta squared over 2mr squared plus b. And if you see, well, you can get every term of these equations if you take the partial derivative with respect to every variable. For example, if you take the partial derivative with respect to pr, you will get r dot. For example, the partial of k with respect to pr, you get pr over m, which is r dot. Okay? So if you get, for example, the partial of k with respect to p theta, you are going to get, well, p theta over mr squared, which is theta dot. Okay? And what happens if you want to take the partial derivative with respect to r or theta? Well, in this case, the partial of k with respect to r is going to be equal to, well, a negative p theta squared over mr to the third power. And then don't forget the b minus the partial of b with respect to r, which is actually this thing that we have here. Okay, we got the same expression. Sorry, I think that here is a plus. Yeah, we have the same expression that relates this with PR dot. So this is equal to negative PR dot, as you can see. And again, the partial with respect to theta of k, well, is going to be, well, just the partial of b with respect to theta, which is equal to negative p theta. Okay, so from these two, we can get that PR dot is equal to negative the partial of k with respect to r, and here p theta, and this is p theta dot. P theta dot equals to negative the partial of k with respect to theta. Okay, so after saying this, well, we can maybe think that, well, there is a function, okay, a function k that I named in this case, that turns out that relates, well, the derivatives with respect to time of the generalized coordinates with the new momentum conjugates that we have introduced. And on the other hand, it relates the derivative with respect to time of the momentum conjugates with the generalized coordinates that we have. Okay, that function is going to be named as the Hamiltonian function. Okay, so right now we are going to define what that is. Okay, we are going to start with general Lagrangian that depends on qi, qi dot, and t. So we are going to get that dl is going to be equal to the partial of L with respect to qi times dqi plus the partial of L with respect to qi dot dqi dot and the partial of L with respect to time dt. Perfect. So from here, maybe we are not able to do too much, but we need to notice that we have a quantity d pi q I dot that is going to be equal to dpi qi dot plus pi dqi dot. Okay, and from here we have that pi dqi dot is equal to d pi qi dot minus dpi qi dot. Okay, and why are we doing this? Because if you notice here, this quantity here, well, is what we just defined as pi. Okay, so we have the product pi dqi dot, which is actually this. So we are going to substitute this for this. And we are going to get that dl is equal to the partial of L with respect to qi dqi plus d pi qi dot minus dpi qi dot plus the partial of L with respect to time dt. Okay, perfect. So what are we going to do now is to take this differential to the right hand side and this term, and this term to the left hand side. So we are going to get minus the partial of L with respect to qi dqi plus dpi qi dot minus the partial of L with respect to time dt is going to be equal to dpi qi dot minus dl. And well, in this case, looking that the operator d is linear, we can set this to be pi qi dot minus l. Okay, perfect. So here is the important thing of the video. That function k that we were working with can be found with this expression that we have here. In general, it will not be named k. Actually, the letter used is h because this function is known as the Hamiltonian function. Okay, perfect. So if we substitute that, well, we are going to get that the Hamiltonian is going to be equal to, well, the differential of the Hamiltonian is going to be minus the partial of L with respect to Qi dQi plus dPi Qi dot minus the partial of L with respect to time dt. Okay, perfect. And just to mention, well, the Hamiltonian function is going to be very, very, very important. If you want to become a good physicist, you need to know what the Hamiltonian function is, because it appears on many areas of physics. For example, in quantum mechanics is very important, and it will be also important in everything that has to be with theoretical physics. Okay, so what you can notice here is that from this expression, well, we can take the partial derivatives of the Hamiltonian with respect to each coordinate or each variable, Qi, Pi, and T. So if we do that, if we see this expression, it's easy to notice that, well, for example, the partial of H with respect to Qi is going to be equal to negative the partial of the Lagrangian with respect to Qi. The partial of H with respect to Pi is going to be equal to Qi dot, and the partial of H with respect to time is equal to negative the partial of the Lagrangian with respect to time. Here, that is very interesting that the change in time of the Hamiltonian is equal to negative the change in time of the Lagrangian. A very curious fact, and will be also very important. But actually, the important results here are these two equations that we have here, that are going to be known as the Hamilton equations. Again, very, very, very important. Perfect. So, well, if we see this second equation, well, we notice first that we are getting the derivative with respect to time of a generalized coordinates in terms of the Hamiltonian and its derivative. But we do not have any Lagrangian function. Okay, the Lagrangian does not appear in this equation, and that is a good thing. But here we have the Lagrangian, so that is not very good. But it's easy to notice that this term here, well, it corresponds to some term in the Euler-Lagrange equation structure. Okay, it's not very hard to remember that actually that term that we have here is going to be equal to negative the derivative with respect to time of the partial of L with respect to Qi dot, just by the Euler-Lagrange equation again. But at the beginning of the video, we defined this to be Pi. Okay, so if we take the derivative with respect to time of Pi, we are going to get that this is negative Pi dot. Okay, so that will allow us to establish the final structure of the Hamilton equations. That is going to be that Pi dot is equal to negative the partial of H with respect to Qi, and that Qi dot is equal to the partial of H with respect to Pi. And this will be finally the Hamilton equations. Again, very, very important in classical mechanics, quantum mechanics, and some other branches of physics. Perfect. So that will be like the final important result of the video.